In this video, I will introduce you to Kepler's three laws of planetary motion. Now, Kepler's first law states that the path of each planet around the Sun is an ellipse, and the Sun is located at one focus. And Kepler's second law of motion is that the line drawn from the Sun, the imaginary line that you can draw from the Sun to any planet, sweeps out an equal area in equal time intervals. So there's this diagram here on the right shows this occurring. So each frame is a given time interval, and the area that's swept out by the planet, so the area of the sector of the ellipse between A, B, and S, the Sun, that area is constant, and also that time interval is constant. Now I've got another animation here, a little more visual, that shows the same idea. Again, Kepler's second law of planetary motion. And so what you see here is that each sector, the area of the sector, is shown on the right hand side, and there's a countdown on the left to show you that the time interval is constant. So the time interval is constant, and then the area is constant as shown in the bars on the right hand side. Now I'm doing this for Earth currently. I can also do this for Jupiter. So another of the planets orbiting the Sun. Again, equal time intervals and equal area swept out. We could do it for Mars, we could do it for Venus. Pluto, the orbit of Pluto is a little more eccentric. So we see it, the more eccentric the orbit is, the more the velocity will change, and in fact the more the velocity will speed up as you get closer to the Sun, because in order to sweep out an area equal to the area swept out at the portions of its orbit further away from the Sun, it must travel faster, because again, in that equal time interval, it must sweep out the equal area. So that's why it travels a little faster. And if we do a comet here, which has a greater eccentricity, this effect is further magnified. So again, equal time intervals, equal area swept out. Alright, so hopefully that makes sense now after seeing those two visuals. And then the third law, Kepler's third law of planetary motion, is that the square of the orbital period of a planet is directly proportional to the cube of the average distance of the planet from the Sun. Now, and so t squared is approximately, or is rather proportional to r cubed for all planets. And so on the next slide here, I'm going to derive that a little more quantitatively, and we'll turn that proportional sign into an equal sign. We'll find out exactly how they are related. So, even though we stated in Kepler's first law of planetary motion that the orbit of all planets around the Sun is an ellipse, to a very high degree of accuracy, the orbits of all the planets, all the 7 outer planets, so with the exception of Mercury, can be described as circular. So the ratio, as an example, the ratio of Earth's semi-minor axis to its semi-major axis is 0.99986. And as you know from pre-calculus, if you have an ellipse that has that ratio, the semi-minor axis to the semi-major axis, equal to 1, that means that the semi-minor axis is equal to the semi-major axis, which means that you have a circle. So if that ratio were equal to 1 for Earth, it would be a perfect circular orbit, but as you can see, that ratio is incredibly close to 1. So it's very close to a circular orbit. So this is true for many of the planets. As I said, the outer 7 planets, with the exception of Mercury. Mercury has a bit more of an eccentric orbit. So assuming a circular orbit, then, we can go back to our last unit on centripetal motion, or rotational motion rather, and we can then describe the orbit of a planet using the centripetal force. And the centripetal force on the planet is equal to the gravitational force due to the sun. And this will actually hold not just for planets, but this will hold for any object orbiting a larger object. So typically we'll call that smaller object the satellite, and the object about which it orbits the central body. So the central body is the object about which the satellite orbits. So the capital M is that the large M is the central body, the little m is the mass of the satellite. So centripetal force, mv squared over r, where the m in the mv squared over r equation is equal to the mass of the satellite. This is equal to the gravitational constant times the product of the two masses divided by the square of the distance between those two objects. So this is just setting the centripetal force equal to the universal gravitational force. And now if we just solve, we see that we have the mass of that satellite object on both sides of the equation. So that drops out. And we then solve for the velocity of the central body, or excuse me, the satellite orbiting the central body is equal to the square root of the gravitational constant, universal gravitational constant, times the mass of the central body divided by the radius. And you see here from this equation that the velocity is independent of the mass of the satellite. Alright, now, as I mentioned, Kepler's third law relates the radius of the orbit, or the average radius of the orbit, to the period of its orbit. And so we want to replace the velocity on the left side of the equation with the period. And we know that period of an orbit, if you have circular motion, is related to the velocity through the velocity is equal to the circumference of the circle divided by the period for one full revolution. And now if we replace that velocity on the left-hand side with the velocity we found by setting the centripetal force equal to the gravitational force, and if we square both sides, we then see that the gravitational constant times that mass of the central body divided by the radius is equal to 4 pi squared times r squared over t squared. And now if we multiply both sides of the equation by the radius of the orbit, and then isolating the square of the period, we see that the period, the square of the period, is directly proportional to the cube of the radius, the average radius of the orbit. And that constant of proportionality we see is in the parentheses here, 4 pi squared divided by the gravitational constant times the mass of that central body. And I'm going to emphasize here, now I'll rearrange this again slightly, that mass is the mass of the central body, and the period is the period of the satellite orbiting that central body, and little r, the radius, is the radius, the average radius of that satellite orbiting the central body. And what we can see from this equation is that for any satellite, whether it's a satellite orbiting Earth, or a planet orbiting the Sun, or a comet orbiting the Sun, that this ratio of the period, the square of the period, divided by the cube of the average radius is equal to a constant. And that constant depends on the central mass of that, the mass of that central body. And this is a constant for all objects orbiting that central body. So for the case of the planets, that ratio of the period, the square of the period divided by the cube of the radius, is the same for Earth as it is for Mars, as it is for Venus, Jupiter, etc. And so this relationship, Kepler's third law, will be used in our class in two major ways. From the first way, you can see that if you're given, for instance, the period of a satellite orbiting a central body and the radius of that same satellite orbiting that same central body, we could then solve for the mass of that central body. Or if you were given either the period or the radius along with the mass of the central body, you could then find either the period or radius. Right? You have three unknowns in this equation. And given two of the unknowns, you could find the third. That's one way we will use this equation. The other way is by realizing that this ratio of a given satellite's period to its radius is constant. So the square of the period divided by the cube of the radius is constant for all satellites orbiting that central body. So I could then ask you, or I could then give you the period of Earth, for instance, the average orbital radius of Earth about the Sun, and then I could give you the period of Mars's orbit, and then ask you to find the radius of Mars's orbit. Or I could give you, the two pieces of information for Earth, and then give you the radius of Mars' orbit, and then ask for the period. In that case, you'll have four unknowns, and I'll need to give you three in order to solve for the fourth. Alright, so tomorrow in class we'll practice using Kepler's law. Feel free to come in with any questions you have about this, and have a good night.